General relativity, step by step. Last time I made a rather impassioned plea not to confuse local geometrical constraints with global topological statements. And I gave an example of a flat space which could either be a torus or the plane, which are topologically different, but have got the same local properties, which is that it was flat space. So having that as a warning, I'm just going to go back and consider this equation here, which was one of the three solutions that we had. That was flat space. We're considering this one as the closed universe. I'll consider this one next screencast, but I'm going to look at this second case just now. So I'm just going to play with this equation here. And we've got this rather nice picture here to bear in mind. Okay, well, let me just write it down. I've got ds squared. I'm going to simplify. I'm going to pinch in a bit more. We've got ds squared equals a squared times r0 d chi squared plus r squared sine squared chi d phi squared, close brackets. Oh, of course, I'm going to specify a equals 1 here, so I'm just going to get rid of that. Okay, right, and chi was equal to r over r0, where r equals the co-moving radius. It doesn't matter that it's co-moving because I'm considering just an instant in time. Doesn't matter. And r0 equals, I guess you could call it the radius of the universe. Radius of the universe. It's quite a nice concept. It's not a sphere embedded in a higher dimensional space. It just happens to have, under this assumption, under this model, it happens to have global curvature, which is like the global curvature of a three-dimensional sphere. Okay, so let me just think about this. What am I trying to do here? Yes, we've got R0. Sorry. What I'm going to consider is I'm going to consider the path distance going around a circle from phi equals 0 all the way around to phi equals 2 pi. So we've got that ds squared equals there should be an r0 there. R0 squared sine chi squared d phi squared. So ds equals plus or minus. You see, I'm ignoring this distance here because I'm ignoring this term. I'm not ignoring it. I'm setting it to 0 because I'm moving around in a circle. So that distance chi, that's chi, which equals constant. Plus or minus r0 sine chi d phi. And of course, the plus or minus is going around one way or the other way, I guess. Actually, no, it isn't. No, it isn't. No, it isn't going around one way or the other. I want the positive square root because I'm considering a space-like interval. You remember that ds squared equals I may as well use the Greek letters. G alpha beta dx alpha dx beta, and we went to great lengths to show that this quantity here can either be positive or negative for space-like or time-like intervals. And I'm considering space-like intervals here. So we only want the positive root. So ds equals r0 sine chi d phi, and I may as well say that the circumference equals the integral of that from phi equals 0 to 2 pi. Well, of course, this term's just a constant, and so what I've got is r0, nope. What I've got is 2 pi r0 sine chi. That's quite nice. Equals 2 pi r0 sine r over the radius of the universe, which is quite nice. And I'm going to expand it as a Taylor expansion. 2 pi r0 r over r0 minus 1/6 r over r0 cubed plus higher order terms. That's just a Taylor expansion. Higher order terms, which I'm going to ignore, equals 2 pi r minus pi by 3 minus pi by 3 times r cubed over r0. You can express it in different ways, plus higher order terms, which is less than 2 pi r. So let me just talk about what I've done. What I want to do, I've got this nice circle of radius r, which is great, and I ask how far around this circle is it in this particular coordinate system. Nothing to do with the expansion of the universe. I picked a particular time, and it turns out that the circumference is less than, strictly less than, what you might expect on the basis of flat geometry. And that's of course because we are considering a space that's like the surface of this sphere here, where the areas are smaller than you would expect. Well, that's quite nice, isn't it? Okay, so that's great. I'm going to stop there and consider the negative curvature case next. Stop.